Yeah. Okay, so we're gonna talk about the third, I guess, stimulus that can trigger the Le Chandelier principle. If you guys remember, Le Chandelier's principle is where if you disturb the system, then it will shift its equilibrium position to counteract that. So last time we talked about how changing the concentration will cause the equilibrium to shift left or right, and then how volume will change it. Okay, volume or pressure. Okay, so we're going to do the last one today, and the last one is going to be temperature. Okay, so if you change the temperature of a system, it's also going to change its equilibrium position as well. So we got an example right here. Okay, so this is at regular equilibrium, and this is this reaction right here. Now we got two different compounds right here. The one right here on the left is going to be pale pink, so it's a pink color, and then the product side is going to be blue. So that allows us to distinguish whether the reactants are dominating or the products are dominating, okay? Now, I want you guys to keep in mind the enthalpy of the reaction. Is this an exothermic or endothermic reaction? If delta H is greater, it is going to be endo. Good catch. Okay, so if, yeah, it's a positive number. If it's positive, that means it's going to be endo because you need to put energy into the system. Okay, so if you heat up this system, if you add heat, it's going to be shifting where? To the left or to the right? To the right. Okay, and the reason why that happens is because remember, if it's an endothermic reaction, energy is going to be a reactant. Okay, since it's endothermic, energy is a reactant. So basically, when you're heating it up, it's like the same thing as adding more reactant, right? So if you heat it up, you are going to be adding more energy, which is a reactant. And so since you're adding more reactants, it's going to shift to the right side, to the products. So that's why it's going to be this blue color. Okay. So it's very similar to changing the concentration. You just do it with energy instead. Okay. And the inverse is true too. If you cool it down, you are reducing the energy. So it's like you're taking away reactants. And so that means it's going to shift towards the left to compensate for that change. Okay. So you can think of change in temperature almost the same thing as changing concentration. The only difference is instead of changing the molecule concentration, you're changing the energy concentration. Okay. Yes. Yes, it would be the inverse. So if it's exo and you heat it up, it'll shift to the left and then vice versa. Okay, good question. All righty. Okay, and that's what this little thing right here is describing for you. So again, just remember, if it's endothermic, the heat is the reactant, and if it's exothermic, heat is a product. Okay. All right, so let's see if you guys remember some terms from previous units. We'll be talking a lot about gases. So I'm going to give you guys about 2 minutes to just kind of discuss with the person next to you. See if you can answer this problem. See if you can use your knowledge of Le Chandelier's principle to explain why equilibrium vapor pressure of a liquid increases with increasing temperature. And if you don't remember what vapor pressure is if you have a liquid in a sealed container, it's going to vaporize even if it's not boiling, and the pressure caused by those gas molecules is called the vapor pressure. Okay, so see if you can figure out why equilibrium vapor pressure increases with increasing temperature. Okay, so take about 2 minutes to write that, and we'll go over it together. Okay, so let's talk about how Le Chandelier's principle explains this phenomenon. So we talk about how vapor pressure is when liquid molecules on the surface of a liquid automatically vaporize into gas, right? So you guys didn't have to explain it this way. As long as you get the same logical flow, it's fine. But I'm going to write a chemical equation just to kind of explain what's going on. So when we have a vaporization or vapor pressure, basically there are liquid molecules and they are going back and forth between gas molecules, right? Now, in order for liquid molecules to become gas molecules, they need more energy, right? So far, so good? So if we represent this but with a chemical equation, we can basically say liquid molecules gain energy, and then they become gas molecules, and then gas molecules basically lose or become liquid molecules, and they release energy in the system. Okay, make sense? Again, you don't need to explain it exactly like this as long as it kind of has the same logical flow. So Basically what happens is if it's at equilibrium, you got some equilibrium vapor pressure. And now what we're going to do is we're going to increase the temperature. Okay, so if we increase the temperature of the system, basically what we're doing is it's almost like we're adding more reactant, right? We're adding more energy into the system. And so if we increase the temperature, what's going to happen is since energy is a reactant, it's going to shift to the right. Okay, it's going to shift to the right in order to mitigate the change in the system. And so if the system shifts to the right towards gas, what's going to happen is you're going to get more gas. And if you get more gas, you get more or less pressure. More pressure, yeah. Just like when you got a fart, there's a lot of pressure down there, right? Sure you guys can relate. All right, so basically some kind of something that has to touches on those points. Basically, the important thing is you got to somehow get to the point where you explain there are more gas, and that'll increase the pressure. Yeah. Yes, you can do that as well. Yeah. Just make sure you talk about Le Chandelier's principle somewhere in there. Yeah, I mean, it says use Le Chandelier, yeah. So if it says something about use Le Chandelier, you have to use it. But yeah, you can, I mean, incorporate that with the ideal gas law, obviously. Yeah. Okay. Le Chandelier.
I'm gonna write that on a test by accident.
Dude, they're gonna think you are so uncultured. Like I'm pretty sure you don't need to remember the how to like write the name, so you should be fine. Yeah. Okay, let us move on. Okay, so we're gonna kind of combine everything together now and try 13.32. I'm gonna zoom in a little for you guys. So basically you have this equilibrium system. Okay, and what you're gonna be doing for this one is you're gonna be describing what happens if all these things are done to the system individually. Okay, so I'll do one of them with you. And then I'll have you guys try the others on your own. Okay, so let's do part A. Okay. So part A, we're doing this one because it's the easiest. Okay, so if we add more N2O4, is it gonna shift to the left or to the right? Yes, you're right. Yeah, sorry, that's my left. Yeah, it's gonna shift to the right. Okay, it's gonna shift to the right. Okay, why is it gonna shift to the right? Exactly. It's because the concentration of the reactants is going to increase, and so obviously it's gonna want to balance that out. Okay, it's like a chandelier. If it swings one way, it's gonna swing the other way in order to mitigate the change. Okay. Okay, so that's how you do it. You're gonna go on to B now and try the rest of them on your own. So yeah, I'll give you guys about 5 minutes to try this one with the person next to you, see if you guys can get them. Some of the ones kind of further down might get a little bit trickier. But yeah, good luck, guys. Alrighty, guys. Yeah. Hey, man's gotta eat. All right. So let's talk about B. So if you remove nitrogen dioxide, which way is equilibrium going to shift? Who thinks left? Who thinks right? All right, you guys are all right. Okay, it's going to shift right. Okay, why is it going to shift right? Because you're decreasing the product concentration, right? And so that means it's going to shift right in order to compensate. Incredible. You guys are the best students ever. I can see Mr. Edwards getting so jealous right now that I have you guys.
Oh,
So jealous.
I'm actually very jealous of how nicely you write with that thing.
Hey, wait. I get criticized for my handwriting all the time. I've been told my handwriting is dog, like almost every day.
Is like giraffe to me.
I appreciate that. Thank you. Giraffe. Wolf. Better dog. All right. Anyway. Okay. So C, I think, was the hardest one. Does anyone want to volunteer their answer? Okay, you have a 50-50 chance of getting it right. All right, Brendan, brave man. Which way do you think? Okay, why do you think it's gonna go left? Okay, somebody, yeah, Billy. Okay, why do you think N2 is gonna be on the product side? Ooh, that's a good thought. Okay. Any other thoughts? I'm not gonna give the answer yet. Yes.
So when you add N2, you're increasing pressure and the reaction will go up, decrease the pressure, and it's gonna shift less, increase more, and it will go forward.
Mm-hmm.
Only has one mole compared to most NO2. Go back.
Okay, for sure. That's a great thought. Any other?
I don't know, I was thinking like the same thing, I know last one about like temperature is like it's endothermic. So but then I was thinking about what side N2 is on, so like.
Yeah.
So I don't know if that's still applies.
So yeah, that's probably the key point. We don't know which side N2 is gonna go on, right? And so if you guys take a look at this reaction, there's no N2, right? And if you guys think back about N2, right? Josie told us about how and nitrogen is what 70 what percent? 78% of the atmosphere because it's very unreactive, right? So N2 actually is not part of this equation. It doesn't go on the left or the right. Okay, so if basically what's happening is if you got a system, you have some amount of N2O4 and some amount of NO2 in there, right? And these guys have their own partial pressures, right? You got partial pressure of N2O4 and you got the partial pressure of NO2. Now it's telling us that we're gonna add some N2 in there. Okay, but what happens to the pressure if you when they add N2? It goes up. So the total system's pressure is gonna go up, which means this nitrogen is gonna also have its own partial pressure. Now, if we add more N2, and that's the reason the pressure goes up, did we change the partial pressure of these guys? No, they have the same partial pressure. So the pressure remains the same. Okay. And so if the pressure does not change, that means it's kind of a trick question. I should have told you. Yes, there's actually no change. Yes. There is no chance. Huh? Yes, you actually had no chance because you didn't know that was an option. Yeah.
Like, so like, it has to do with partial pressure, not like.
Yeah, partial pressure, because if you remember, at equilibrium, the ratio is going to depend on the partial pressures of just the two gases, right? The ratio between these two did not change. You threw something else in there, but it doesn't affect the ratio of the two that were already in the system, right? Yeah, if it's not part of that, it's not going to affect it. Now, if the pressure stayed the same, that means something must have changed, right? But here it tells us when you added more gas, the pressure increased, so we can assume that the partial pressure is the same. Yes. If it was part of the equation, then yes, it would shift to the left. But since it's not part of the equation, it's not gonna do anything. Yeah. So yeah. Make sense though?
Yes.
See, like I said, guys, I want to bring you guys into despair. You had no chance of getting that right. I did. Wait, how long is he cooking that? I think he took it. Okay. Or there's gonna be it's gonna burn. Okay, let's go to part D. D is more manageable. Who thinks that it shifts left? Who thinks it shifts right? Yes, it shifts right. Great job, everybody. Okay, so it shifts right because obviously if you're going to decrease the volume, what's going to happen to the pressure then? Oh, sorry. Yeah, pressure increases or volume increases. What happens to the pressure? Pressure goes down. So it's going to want to up the pressure again. So it's going to shift to the side with more gas molecules. Okay. Sorry about that, guys. I got all confused talking. Yes, exactly. Exactly. Yes. Yes, because there's more moles. More moles of gas on the right. All right. Last one, part E. Temperature is decreased. Now, if you take a look at the enthalpy, is energy a reactant or a product? Yeah, it's a reactant. So I'm going to write E for energy. Okay, so if we take away energy, it's basically saying that we are removing reactants. So it's obvious going to shift to the side that to compensate. It's gonna shift left. Okay. All right. So it seems like most of you guys got every one of them except C.
Stupid trick question.
Okay. Well, if you got 4 of them, that's a 5. If you got 3 of them, that's a 4. So great job, guys. You guys all.
She just said it.
It means you're illiterate. Yeah.
Was meant to do something else.
If it was something that changed the reaction or was part of the reaction, then yeah, it would shift it left or right. But because this is not gonna react with either of these, it's not gonna change it. Also, it's because when the pressure increased by the addition of N2, so that means the partial pressures here did not change. Yeah, yeah, that one's a toughie. Evil, just like me.
So it has like what's it like that on that's like well, you just have to like right left or right or is that like
No, you can write no change or no shift. That would probably be more of a multiple choice question. Yeah. Okay, let's go on to the last thing for this unit. We're gonna do one practice problem and then we'll be all done. I know, incredible, right? Yay! Okay,
That was so big.
sorry. Oh, I was also being so real. Are you assuming my intentions?
it's so real.
Dude.
You know, like easy though.
It's kind hey, wait, hey, you guys say that and you're gonna take the test and be like, I hate this unit. No, it's all good here. Don't worry, Bailey. Once they see the review and they start seeing the problems, they're not gonna like it either. Yeah, you're just ahead of the curve right now. Yeah. All right. Anyway, catalyst. So we know catalyst from kinetic to kinetics unit, right? Basically, you just reduce the activation barrier between reactants and products. Thanks, guys. You can just leave it right there. Okay. And so basically the catalyst only changes the rate of the reaction. Okay, we learned last time that the catalyst does not change the final energy level of the reactants and products, right? It just changes the rate and the activation energy. Okay, so what that means is when you use a catalyst, it changes the rate of the reaction, but this is the key thing. It does not change the value of K, okay? It does not change the final ratio between the products and the reactants. Okay, so that's the key thing to note. Okay, you can throw a catalyst in there. It'll help the reaction go forward and come to equilibrium faster, but it will not affect the final state of equilibrium. Okay, yes.
Just making sure it increases like the rates of the forward reverse evolution.
Yes. Or no, because depending on where they start, what energy level they're at, it's gonna have a different numerical change. So here, it's gonna be the activation energy is gonna be lowered less than here because of the difference between these, yeah, the reactants and the products. But it'll change the rates similarly.
So would this be like a problem when they said, oh, with like the graph or something?
They'll have you analyze a graph most likely. Yeah. Do you have a question, Claudia? Okay, I thought I saw a hand though. Can't see very well, sorry. Okay. Yeah, so the key thing is the uncatalyzed reaction is slower. Catalysts just speed up the reaction, but the final state of equilibrium, if you look here, the equilibrium state is going to be the same. Okay, catalyst just helps you get there faster. Interesting. Okay, and that's it, guys. Woohoo! We're just gonna combine everything together and do one long problem together. So much fun. Okay. You guys want a 5-minute break? All right, we'll take a 5-minute break. Think so. 14. No better than me. Wait, isn't it 15?
14. It's 14 together. I didn't explain.
Right.
Like review.
Yeah, we're gonna do a full month of review. Yeah. Yeah. Sure. Alrighty. I believe it. I want you all to get a 5. I do, except you. Okay, so 11 or 12:33. So sorry, Brandon. You just keep setting me up for that, man. Just tossing me those lobs. Okay. So this is our I guess scenario that we're looking at. So at temperatures near 800 degrees Celsius, steam is passed over hot coke, not that coke, It's a form of carbon obtained from coal, and it reacts to form carbon monoxide and hydrogen gas. And you see the reaction right there, okay? So this mixture of gases results in an important industrial fuel called water gas. That's not too important, just some basic info. Okay, this is the part where we start the problem. It tells us the equilibrium constant for this reaction at 800 degrees Celsius is 14.1. So that's going to be the equilibrium constant. Again, the ratio between reactants and products in this system at equilibrium. And then it's asking, what are the equilibrium partial pressures for these three gases if we start with solid carbon and 0.1 moles of H2O in a 1 liter vessel? Okay, so we'll start with that. Alrighty, so what we're basically doing is we're going to be using this information to figure out the equilibrium constant. Okay, does anyone remember what type of problem this is? I heard it.
Combustion.
Well, yeah, it's not combustion. I heard ice
Oh,
table. Yeah, ice table.
But it was a type of reaction.
Oh, no, I said type of problem. Yeah. Yeah, type of problem. I'm sorry. It's not a combustion reaction. Okay. Okay. So this is going to be an ice table problem. So I'll give you guys a minute to set up your ice tables. Okay, so just keep in mind, anytime you need to calculate equilibrium constant or equilibrium concentration, most likely going to be an ice table. Ah. Alrighty, so we got our ice table, and now we got to start putting in some information. So here it's asking us, what are the equilibrium partial pressures? So that's basically what we want to find. Okay, and it gives us some information. It says we start with solid carbon and 0.1 moles of H2O in a 1 liter vessel. Now, we know that in the ice table, we typically put things in molarity, right? Okay, but if you look at the problem, it's asking us to find partial pressure, which means what's the unit of measurement we're probably going to want at the very, very end?
Pressure.
Yeah, pressure, which is ATM. Okay, ATM. All right, so we want ATM, and so we haven't done this before, but in ice tables, we can actually put everything in terms of ATM. So we can take this information right here, turn it into ATM, and then we can put it into our problem, okay?
You just need to say.
No, that's from molarity. So we're gonna use the ideal gas law in order to find ATM here, okay? So based on this information, I want you guys to calculate the pressure, the partial pressure of H2O at the beginning of the system, and then I want you guys to plug it into the ice table, okay? So this ideal gas law, we're gonna use it in order to find the partial pressure of H2O. I'm gonna put that in the ice table, okay? Alrighty, guys. So we are going to use our 0.1 moles of H2O in order to find the partial pressure of water in this container. So we start with 0.1 moles, which is going to be for our N right here. Okay. And then we're going to multiply it by the ideal gas constant, 0.0821. And then we're going to multiply it by 800, right? 800. Yes. Yeah. Just checking. Yeah. You want to convert it into Kelvin. So it's going to be 1073. Okay. So you should get a partial pressure of, I'm going to round that up to 8.81. Okay. Everybody good with that? Okie dokes. And that's going to be in atmospheres. All right, now we got to fill in some of the information for the other initial. So since we don't know anything about the products, we can say that we have none of it. Okay, what should we plug in for the solid carbon? Because we start with solid carbon, but we don't know how much. So what should we put here?
Pure substance.
Yeah, it's a pure substance, so it doesn't matter for equilibrium. Okay, so yeah, keep that in mind. I know it was a long time ago now, like 2 weeks ago. Pure solids, pure liquids, they are not taken into account for equilibrium. Okay. All right, so from here, it's just a standard ice table. Are we gonna have a positive or negative change for H2O? Negative. Negative, yeah, because we're gonna lose some, and that's gonna end up with 8.81 minus X, and then obviously we'll gain for the products because we didn't have any in the beginning. Okay. All right, so that is going to be our equilibrium concentration, and we just need to calculate that out. Okay, so we know the Kp value is 14.1, and that's going to equal the concentration of CO times the concentration of H2 divided by the concentration of H2O. Okay. Seems like some of you guys are still working on it already. So we're gonna plug in our values. So for CO, it's gonna be X. H2 is X. And then H2O is 8.81 minus X. Okay. All right. So unfortunately, what does this look like? Yeah, we're gonna have to set up a quadratic here. So you could test the 5% rule, but I'm gonna let you guys know right now, it will not work. It will not pass the 5% rule, unfortunately. I'm so heartbroken for you guys. Usually you'll have to figure it out with the 5% rule. So typically, like if I didn't tell you just now, you could ignore this, and then you can. Yeah, and then test it, but I'm just gonna let you know at a time. It's not gonna work. Yeah. Yeah, you can't. Unless you're like a human calculator. You have to do the calculation to figure it out, unfortunately. Okay, so I'm gonna give you guys about 7 minutes to try this out. See if you guys can do the quadratic and figure out the final partial pressures for all of the gases. Okay, again, you're gonna need to know the quadratic formula, and I'll write it up here. No, negative Q. Wait. Don't mess me up. I'm trying to do it without seeing it.
Mine's going. Oh, mine's going C.
Okay. I don't like singing, guys. Like I said, music isn't real.
What do you mean?
Okay, so I set up the quadratic for you guys. Basically, just simplify this equation, and you should get this right here. Okay, and then I plugged it into the quadratic formula. Okay, so what we're gonna do now is we're gonna start solving it part by part just to make sure we are all on the same page. So let's start with 14.1 squared. 14.1 squared, and that's gonna give you 198.81. Okay, so that's gonna be that part. So 198.81. Okay, then we're gonna do the other stuff inside, or we'll do the 4 times that stuff. So we'll do 4 times 1, so obviously 4, and then 124.22. And since that's a negative, we'll get negative 496.8. Negative 496.88. Okay. So far, so good?
Yeah.
Okay, now we got a negative and a negative, which becomes a positive. So we're going to add these two values together. So we're going to add 198.81 to that, and that's going to give you 695.69. Okay. Okay. And then we're going to find the square root of that. I guess do I have that function on this? I do. Haha. 26.38. Okay, so if you find the square root of that, you should get 26.3. All right. So far, so good? Okay, glad to hear it. Okay, so obviously 2 times 1 on the bottom is going to be 2. So now we have our operation. It's either going to go positive or negative. Now, just by looking at it, you can kind of tell which one will make sense and which one will not make sense. Hello. Why are you ditching class? All right, so here, obviously we're not gonna subtract because that'll make the number even more negative, right? And so you're not gonna want to do the subtraction. So without even solving the problem, we can already assume that it's not going to be negative. So we can just add the negative. And so basically what we're going to be doing is 26.38 minus 14.1. That'll give you 12.28. And then you got to divide that by 2. So you should get a value of 6.14 for x. Okay, so if you guys got that or something similar, then great job. Okay, you are prepped for, yes, the quadratic. Great job, everybody. Okay, so let's plug in our values because we're not done. We need to find the equilibrium pressure. So 8.81 minus 6.14 is going to give us 2.67 for the pressure of water vapor. Okay, and then we're going to have the same equilibrium pressures for carbon monoxide and hydrogen gas. And there you go. That is going to be part A. Fun. Yeah, that was part A.
Great.
All righty. Any questions about that one? All righty, let's move on. If you guys got this all copied down. Okay, we're gonna go to part B now. All right, so in part B, it's asking us what is the minimum amount of carbon required to achieve equilibrium under these circumstances or these conditions. So basically, what's the minimum amount of carbon that you need to reach equilibrium like this? Okay. So for this, we're gonna need some of the information. So just make sure you guys have it set up. Basically, this is just regular stoichiometry from here on out. Okay. So we can pick one of the partial pressures to work with, and then we can use the ideal gas law to turn it into moles, and then we can use the mole ratio and do molar mass. Okay, so if that makes sense to you, great. If not, I'm gonna go through it step by step. Okay. So which gas do you guys want to use? CO. Okay, we can use CO. Okay, so what is the partial pressure of CO in our equilibrium system? Exactly. So 6.14 ATM. My favorite J. Cole song. Anyway, ATM. So we're going to use the ideal gas law in order to find the moles. So we know that the ideal gas law is PV equals nRT. So I'm going to give you guys about a minute or so to solve for the moles of carbon monoxide. And then Miles, this is all recorded, so you'll have I'll put it up after class today. Also, did you like my message? Yeah. I was so disappointed today because clearly Europe's no good.
Sorry.
It's okay. I'm used to it.
Looks like you were like skipping class with my
So if you plug in your values for the ideal gas law, you'll get this value 0.0697 for your moles of carbon monoxide. Okay, now one thing I do want to mention before we move on is that I know that we picked the partial pressure of CO, and that's totally fine. We could also have picked the partial pressure of H2, but we could not have picked the partial pressure of H2O, the final partial pressure, because what matters is how much of these gases we made, right? And so here we would have to look at the change, the difference in H2O. So you can still choose H2O, you would just have to be able to identify that we lost that amount of partial pressure for H2O, okay? So just keep that in mind. Okay, so we're gonna take this value and we're gonna calculate the amount of carbon that's needed to produce this amount of CO. So we're gonna take 0.0697 moles of carbon monoxide. We're gonna set up our fraction. Okay, our mole ratio is 1 to 1. Thank the Lord, makes our lives easier. And then the molar mass is also very easy. It's gonna be 12 grams of carbon. So all you gotta do is 0.0697 times 12. Okay, and we'll get a final mass of 0.8. I'm gonna round that up to 4 grams of carbon.
Would it be like a negative moles if you find it?
Usually amount is referring to grams, and so you're gonna want to give it in grams. AP test will probably specify whether moles, grams, or whatever, but if you ever see amount, I would recommend just being safe and going to grams.
So in most cases, probably if you did do a whole,
Yeah, you probably get partial credit. Yeah, definitely. Yeah, because then it's just a, it's just a molar mass fraction.
So they give you partial credit for like the FRQs, but like if you do your work correctly, on multiple choice, but
They don't look at them. Yeah, they don't look at the work from multiple choice. Yeah, it's one and done. It's cold blooded. All right, let's move on to C. Okay, so total pressure of the vessel at equilibrium. So this one should be pretty simple. You guys should remember that total pressure of a system is equal to the sum of all the partial pressures. So basically, you just need to find out the partial pressures of all the gases at equilibrium. We could have done this right after the ice table, but they gave it to us here. So let's solve that together. So the total pressure of the system is going to be equal to the pressure of the water vapor at equilibrium plus the partial pressure of carbon monoxide plus the partial pressure of H2. Okay, so you just need to go to the bottom column or row of your yeah, no, go ahead. What's it? Pretty sure? Okay. Yeah, just look at the bottom row of your ice table. And then you get 2.67 ATM plus 6.14 ATM plus 6.14 ATM. And that's going to give you a total value, a total pressure of 14.95 ATM. Okay, so that one is probably the easiest one out of all of these. All right, so far so good? Okie dokes. All right, let's move on to part D. So in part D, it says at 25 degrees Celsius, the value of Kp for this reaction is that right there. And it's asking, is the reaction exothermic or endothermic? Okay, so this is a kind of like a Le Chandelier principle. So I'm going to give you guys about 2 minutes to kind of think about it, see if you can write an explanation. Okay, this one is 50-50. It's going to be exo or endo. It's not going to be some neutral, non-thermodynamic reaction, I promise. So just based on the information that we have, I want you guys to see if you can figure out, is this exo or endo? I promise it is one of them. Okay, so for this problem right here, we're trying to figure out if the reaction is exo or endo by looking at the value of Kp at a different temperature, okay? So let's just compare the two. So the original system that we have, what's the temperature that we had in the system we were looking at before? Yeah, we had 800 degrees Celsius. And they said that at 800 degrees Celsius, the equilibrium constant is 14.1. Okay, we're going to take a look at the new system now. It's going to be the temperature at 25 degrees Celsius. So if we take a look at what happened, did the temperature increase or decrease?
Decrease.
Yeah, decreased a lot, right? So the temperature is going to decrease. All right, and so if we take a look at the new equilibrium constant, it's going to be 1.7 times 10 to the negative 21. Okay, and so yeah, the Kp decreases a lot, right? Okay, so based on this information, we can kind of think about what happened. So if we take a look at the Kps, that's going to tell us whether or not the reactants or the products are going to dominate, right? So at 800 degrees Celsius, do we have more products or more reactants? Yeah, obviously more products because we have a number that's greater than 1, right? So that means the products are going to dominate at 800 degrees Celsius. Okay, but when we drop the temperature, what happens here? Do we have more products or reactants? Yeah, we're gonna have a lot more reactants when you decrease the temperature. Okay. Okay, so the assumption that we can make is that when you decrease the temperature, okay, is equilibrium going to shift to the left or to the right? To the left, yeah. To the left, to the left. Everything in a box to the left. Okay, so it's telling us if you decrease temperature, if you get rid of energy, it's going to shift to the left. So if that's the case, is energy a reactant or is energy a product? Okay, so those are the two options. Okay, so if we take a look at this right here, okay, we're getting rid of energy, right? So we're losing energy. Okay, so let's write that down. We're gonna lose energy. And if you lose energy, are you making more reactant or more product? Yeah, more reactant. Okay, so if you make more reactant, that means is the system making energy or getting rid of energy? Yeah, it's making energy. It's putting energy into the system. It's okay. It's okay. I love the confidence. Okay. Okay, so you're making energy. So that means energy is going to be a. Are you guys sure? No, it's making energy to overcompensate for it. So if it's shifting left, it's energy on the equation. Is it on the left side or the right side? It's on the left. Yeah, because it's going to shift to the left, right? It's going to shift to left, so there's more energy in the system. So energy is going to be a reactant in this system. Okay? So think about it. So with the equation in mind, think about it. If we get rid of energy, we're losing energy, right? This is disappearing. If it disappears, we know that the system is going to shift left, right? In order to make sure that we don't lose too much. And so this is how we know that this is going to be an endothermic reaction. Yes.
Like relate that to the side of Does the energy like at all factor into how large the test is?
The energy itself doesn't, but because it's a reactant, the energy is gonna affect the concentrations right
So,
here.
like, you see, like, there's more react.
Yes, you're gonna wanna say, yeah, reactants, yeah. You don't wanna say anything like energy is gonna cause the KP to change. The energy is gonna cause the concentration of the reactants, yeah, and that'll affect the KP, yes. And maybe that was the wrong way to say it. Making energy is not the right way to say it. So if the system is losing energy, it's going to need more energy, whichever side it's on. Yeah, I'm sorry, Sammy. That making is probably the wrong way to word it. It's probably confusing. Sorry about that. Yes.
So it will affect the product.
Hmm?
So it will affect the product.
The concentration of the product, yeah.
So that's what it's filtered.
Yes.
So what are we supposed to do around? What if it is an example of the product? It will affect
Energy is a reactant. Yeah, so just to clarify, just to get the chain of thought is that when the temperature decreases, you're shifting from the right to the, so you're going from a product dominated system to a reactant dominated system. So as you decrease the temperature, right? As you decrease the temperature, what's happening is it's shifting to the left, right? So you need more reactants. Does that make sense? And so energy has to be a reactant because it needs to shift in the direction to mediate the change. If you shift it to the right, then you would actually, the system would be creating more products, right? And so energy has to be a reactant in order to compensate. Okay. All right, last one. Okay, and this is a Le Chandelier principle. To produce the maximum amount of I'm gonna get rid of this. I don't need you anymore. To maximize the amount of CO and H2 at equilibrium, should we increase or decrease the pressure? Okay, so I'm gonna give you guys about a minute, see if you guys can think about it and figure it out, and then we'll go over it together. Okay, so it says in the system that we want to maximize carbon monoxide and hydrogen. So you want to make as much of the products as you want. So do you want the reaction to shift left or right?
Right.
Yeah, you want it to shift right. Okay, you want it to shift to the right. Okay, so if you want it to shift to the right, are you looking to create more gas molecules or fewer gas molecules? More. You want more gas molecules. Okay, because there are 2 on the right side and 1 on the left side. Okay. So if you want more gas molecules, should you decrease or increase the pressure? If you increase the pressure, you're going to want less to mitigate that change. So you want to decrease. Okay, you want to decrease. Because think about it, guys. If I get rid of the pressure in the system, right? If I make the system bigger, right? If I increase the volume, the system is going to create more gas molecules to minimize the change in the pressure. And so it's going to force it to shift right. Okay, and so that's why you want to decrease the pressure. If you lower the pressure, in order to reduce that change, you're going to create more gas molecules, and then that's going to shift it right, which is the outcome that you wanted. Yeah.
Like I get that, but once you add those gas molecules, isn't the pressure going to decrease?
You're not adding any gases though. The gas molecules already in there start creating more.
No, I know it's gonna be like tricky.
Uh-huh.
Is that gonna like cause the pressure?
Yeah, but it'll never be as high as the pressure that you had before. If you look at if you look at the Le Chandelier charts, it tells you that at first there's going to be a drop in the pressure, but then it's slowly going to increase, but it's never going to be at the same level it was before, because you don't have enough gas molecules, or the system is bigger now, and so it can't fill it up with the same amount of pressure. So at first there's going to be a sudden drop in pressure, and it's going to increase a little bit, but it's never going to get past the amount that there was. That makes sense? Yeah. Yes, correct.
I thought it was right. Would you put in